Hi, welcome to the Signal Path. In this episode, I have another repair attempt for you guys. This is an Agilent E4443A 3 Hz to 6.7 GHz PSA series spectrum analyzer. Now, the PSA series spectrum analyzer is not that old, and there's a lot of them in service still, and these can be configured all the way up to 50 GHz. Obviously, they wouldn't have a Type N connector anymore. They would have a V connector, but nonetheless, this is something that's still in use, and then the PSA became a PXA, and then the UXA version with the new GUI interface came out and so on. But this runs a Unix type of operating system, doesn't run Windows. And it's fairly old looking nowadays, but a lot of labs still use these. So this is probably the most complex instrument that we're going to be trying in the lab to repair. This I don't have a schematic for it, but I do have some block diagrams from the service manual. And there's tons and tons of stuff in here. It's very, very heavy. I would say maybe 30 to 35 kilograms. It's quite heavy. That would be about 65 pounds. And a lot of options, a lot of capabilities. Obviously, it's a pretty expensive instrument even now. Even the one at 6.7 gigahertz is still pretty expensive. So it's going to be interesting to see what we can do with it. Now, in terms of how we go about doing this repair, obviously taking a look at the service manual is going to be useful, but we can see what kind of errors it's generating. So it's a system alignment, all align, needed, and it periodically tries to align, and it fails. And if you look carefully, you can see that we are actually recording this from the future, and yeah, things aren't so bad. And the reason we are recording from the future is because the battery has died, so every time it reboots it goes to 2033, which is somewhat unusual. Normally they reset back to 1970 or so. I'm not sure why it's doing that, but anyway, if I go under system and I go under show errors, you can see just a whole bunch of different errors being generated here, and these all have to do with alignment. So wideband IF ADC failure there, align RF gain is failed, measuring of the comb filter is failed, the 312 megahertz amplitude curve has failed, and if I go into the next page, ultimately you see the second LO power has also failed. Now normally this type of cascade failures of alignment may have to do with something with the LO structure, because the internal LO of the instrument is essentially what is used for some of these or most of these internal alignments. And there are a lot of ADCs and DACs in this that set various calibrations and so on, and some of those could be bad. It's very complicated. So I'm not sure if we can fix it, but certainly it's going to be very interesting to take it apart and take a look inside and look at the block diagrams. For sure, there's going to be a ton of learning just from doing that, even if we can't fix it. So let's go ahead and see what we can do. Maybe take a look at the service manual would be a good place to start, and I'm very eager to see what's going on inside. It's difficult to maneuver. Hopefully I can film it to the best of my abilities and see what we can do. It's going to be an interesting one. So let's go ahead and take a look at the block diagram of the instrument. Now obviously there's tons of stuff here. We're going to focus on block by block, and this particular one is for the E4443A, which is the unit we're going to be looking at. So it's zoomed out a lot, so let's go ahead and take a look at the very input, which is the RF input, and we can then track and see what's going on from there, following the signal path, no pun intended. So here the RF input goes through an input attenuator, and then an optional second attenuator gives you a much higher dynamic range and so on. And I'm not actually, I take that back, none of these are options. They actually both need to be there, considering that the front end one doesn't have a lot of attenuation. It actually also performs a different function. If you look over here, there's a 50 megahertz minus 25 dBm calibrator signal that can be injected into the front end attenuator. Now this is a nice thing to do because it means that you're able to actually fully characterize the attenuators all the way through here. The attenuator steps can all be characterized, and this is critical if you want to make sure the attenuators are there and the steps are consistent, and if anything happens you can detect them. So one of the ways that an error will be generated in an instrument is that if this calibrator signal is not present, it's not at the right frequency, or it's not at minus 25 dBm. So this is one of the places where we can check to see if there is an issue. If I follow that forward, we're going to reach the A19 unit, which is the rhythm, which is a routing gig-tuned harmonic mixer. This is the high band portion of the instrument. So above a certain frequencies, it will be processed by this section. And if you look carefully here, you can see the LO coming into it should be between 3 to 7 gigahertz, and it has to have a 14 dBm power on average. So that's a lot of power. So if this is not present, you're going to have a whole bunch of other errors. Now, there's a switch in the front here, and the gig-tuned filter driver coil is also on this block, coming from some other circuit. Let's not worry about that right now. So depending on the frequency range of operation, you either go through the gig-tuned filter to the mixer or you don't. If you don't, then you go through the electronic attenuator at the very top. Going forward over here, we have a 3 gigahertz low-pass filter, which makes sense because this is a low band. Going through a low-band preamplifier, if that option is there, and I think this instrument might have it, I haven't checked.
Anyway, if you do, then you're going to get the preamp, which is nice. And I've talked about preamps and their impact on noise floor and instrument noise figure before a lot. So here you can see you can bypass it, or you can get another 20 dB minus 5, 40 dB minus 5, so about 30 dB of additional gain, some protection inputs, and so on and on. Nothing unusual. Then you're going to reach the low band portion. So all of these are RF sections. But what about the LO section? Now if I go back over here and pay a little close attention here, we see that our block A18, which is the Yick-tuned oscillator, is also part of this LO distribution network. Now this entire section is controlled by the A13 front-end driver, which is one big board that controls all the attenuators, controls all the switches for the mixers and low band and high band. Everything is handled through here. Now if I follow over it again, you can see that our Yick filter, Yick oscillator signal goes into this A21 LO distribution amplifier. Now this is a critical block. And these are all custom blocks, by the way. And this block is important because it distributes the LO signal from the oscillator, from the Yick-tuned oscillator. So you can see that there is a front-end attenuator, some amplifier, then we get a high and a low band section, and then we get the first LO out. We get a sampler out, and we get the pin attenuator in. So the LO amplitude can be adjusted. That's LO leveling. The sampler out goes into some other block. We're not going to take a look at that right now. Here's the high and the low LO. Meaning that when the instrument is in high band mode, you can see that the high LO will go into this block over here, which we just talked about, the rhythm block. And then if it's on the low, it will go into this section, which is the low band portion. And the low band, of course, gets its RF signal coming from the section we just talked about, from the preamp. So it all makes sense. So let me change the color in here so we can get a little bit cleaner here. So if the signal is in high band, it's just going to go through here. I'm going to go down, and it's going to go this way. If the signal is in low band, it's going to go over here, it's going to go through here, then it's going to go through here. So at the end of the day, you're going to reach two places, one here and one here for the high band and the low band. And then the LO signal is going to be distributed, as you can see with these two arrows, either in this portion or in this portion. So the block diagram begins to now make sense of what signals we want to look at. Now, if I continue this, you can see the low band is going to need its own LO signal, it's going to need its own second mixer and so on, so that the signal will eventually get to the same point and be processed by the third converter. All of these instruments essentially do the same thing. They have a high band and a low band processed into two different sections, but then ultimately they will all reach the third converter to be in the same location, which makes sense because we don't want to replicate that again. This is the portion where it's going to be in the hundreds of megahertz. So let's look and see where the LO comes in now. If you remember, one of the errors of the instrument was second LO power, which means the second LO power was bad. So now we need to want to look at the second LO. The first LO is in here. I didn't see an error for the first LO, so it's likely that it doesn't have an issue, which means that we can focus on the second LO. Now if I go over here, here's our second mixer. Therefore, it's going to need a second LO. Here's our second LO gain adjustment. So the second LO is entering from here. That's pretty useful. Now we can also see that there's a 7.2 gigahertz notch there, and I keep wanting to make these quizzes, but for you guys to answer. But you know what? Let me just tell you what's going on. So the signal coming here is 3.6 gigahertz, coming at 3 dBm. So they put a notch filter in here, so the second harmonica doesn't enter the second mixer. And if you go over here, we have a second LO board. This is a good place for also to investigate. So if you look at this second LO board, it has an interesting structure. The input to it is from the reference board, the reference synthesizer of the entire instrument, where the 10 megahertz or the 30 megahertz, 1 megahertz to 30 megahertz reference actually comes in, or the 10 megahertz reference comes in. So this is the main synthesizer board. We don't get an LO on lock, so this is probably working. But we have a 600 megahertz signal entering the second LO board, and the second LO board will lock that using an internal DRO, the electric resonant oscillator, and that's going to generate a 3.6 gigahertz 3 dBm signal. So that's our second LO, and it's got some interesting fan control is also on the same board for whatever reason, and that will then be the 3.6 gigahertz going to the second LO section. So there's tons of places for us to take a look at. So I've already pointed them out, so let me just mark them again with a different color. So a few things for us to test from the very beginning. Let's go ahead and test, make sure our calibrator signal is present. That's pretty important. Let's go and make sure our LO signals here are present. That should be pretty straightforward and easy to test. Let's go and make sure that our 600 megahertz signal is present. That's also important. And of course, finally, let's go and make sure that the second LO is present. If checking these will tell us a lot of information about which portion of the instrument might be having a problem. And that's obviously what you'd want to do. You'd want to test signals within the different modules, not inside the module, in between them, because inside them you have to take them out of the unit. So there's a ton of stuff to go take a look at. As you can see, I only spoke about a small portion of it. And if these are all working fine, then we'll dig deeper and deeper into the block diagram. But ultimately, this is the strategy for me to follow. There's a couple of places to take a look. Now, obviously, we need to go back to the unit and figure out which of these blocks is what once we take the instrument apart. But it should be pretty exciting to try and look at these signals and see if they have the correct value. So back to the instrument, see what it looks like.
All right, after removing about 4,000 screws, there we are. Now I've taken the top cover off. I haven't touched anything else, but everything is in view so we can make some judgments about what's going on. So the input obviously comes from here. This input here is right over there in the corner of the screen. You can see it. I have now a Type N to SMA converter there. Goes into there. Here's our first attenuator. Here's the 50 megahertz signal being fed also into the attenuator. So you can see the attenuator can either choose to process this or process this. And then that's passed on to this cable to the second attenuator. The second attenuator output comes over here and goes to the rhythm, the routing YIG-tuned harmonic mixer. On the other side, here's our YIG-tuned oscillator. Right over here, you can see that it goes into this LO distribution network, which I was talking about before. Here's the high LO. Here's the high LO, here's the low LO, and here's the sampler output. And this first LO output is actually terminated down to 50 ohms because this instrument doesn't have the option for the LO output populated. But interestingly enough, you can actually do this yourself. We can add that option to the instrument ourselves by bringing this to the front or to the back, wherever it's supposed to go. So I might actually add that option if I can fix it. Then continuing from this, we can see that our second LO portion over here, this is a second LO board, so which is going to require the LO from the 3.6 gigahertz LO from the other LO generator. And if I follow that, we can see that that one is right over here. There's another block sitting here which generates the other LO. So the points of interest that I wanted to measure was measuring here, making sure LO comes out of this at sufficient power, measuring this to make sure LO comes in here at sufficient power, and measuring this to make sure the 50 megahertz tone is actually entering the instrument. So doing all of these things would be the points that I mentioned there. And we see we don't really have to take anything apart because they're all connected to each other quite nicely. But the different sections are very, very clear. The harmonic mixer here, the second LO converter there, very visible YIG, YIG-tuned filter, LO distribution network, second LO generator, synthesizer board, very straightforward. So let's go ahead and start doing some measurements. I would suggest measuring the LO first. That should be fun. So by the way, there is a second repair going on right now. So sitting over there, and I'm waiting for some parts for that to come so it can be completed. So I'm going to give you guys some internet points if you can tell me what instrument that is. Of course, the front panel is not there. So that's going to be pretty interesting too. Working on that, looking for some parts to arrive. And then so in the meanwhile, we're going to be focusing on this one. So right now it's turning on, it's booting. So slowly, obviously, it's going to go through a lot of, as you can hear, a lot of attenuators clicking, a lot of alignments it's trying to do and it can't do. And once that's done, we're going to try looking at a couple of things. Like I said, now I know I went through this fairly quickly. I'm not sure, to be honest, sometimes I feel like I go faster and faster as the videos have progressed over the years. So you have to let me know if it's too fast or if you want me to focus on something in particular. But I went through this fairly quickly. And if you watch my older videos, some of those I go over these much slower because I assume that my regular visitors and viewers have some experience with these things also. But your feedback is always appreciated. So I was just about to do some measurements and I was looking at the screen and there's some interesting effect here that I was ignoring before. So if you look here, you can see the noise floor is low and then there's a jump and then it goes higher. Now this is not that unusual for a spectrum analyzer. That's because when it switches bands at different mixers, sometimes it's jumping on a different harmonic and the overall system noise is higher. So you will get a higher noise floor. That's not unusual, but the fact that this jump is here, I thought let's do a quick test to see if this is normal. So what I can do is I can put a signal into the spectrum analyzer. Right now I have the input of this spectrum analyzer like that, connected all the way over here to my Keysight EXG. So right now it's set to 1 gigahertz, and we can try setting it to somewhere at a much higher frequency. Let's set it to 6 gigahertz. and the amplitude is 0 dBm. So we can go ahead and enable that and see if we see the signal on the instrument. There's enable, and there it is. It says final IF overload. Let me change the span here. It's probably not calibrated very well. 10 dBm. Yeah, it's definitely not calibrated. It's got some really weird noise going on there. So let's go ahead and take a look and see what it says. Where's our peak search? There it is. It says 2 dBm. Yeah, it's not quite right, but that might be because of the alignment issue. So you can see the signal is definitely there, and it's measuring roughly the correct power, and so it's working around this frequency. So let's go ahead and try reducing the signal to just 1 gigahertz at a time. So let me see. So this is 6 gigahertz, now 5 gigahertz. Still fine. You can see it's peaking it. 4 gigahertz, and then 3 gigahertz, and it's gone. You can see that it disappears. So indeed, there is a problem, and this is the low band portion, and this is the high band portion. So it looks like in the low band portion, the signal just vanishes, which is somewhat consistent with what we were saying. Actually, one of the measurement points that I was looking at was the LO signal into the low band section. So that's actually a good place to start instead of looking at the 50 megahertz input, because we do have this section working. This section depends on the high LO signal, but this one depends on the low LO signal. So let's go ahead and take a look and see if we indeed get the LO signal going into here.
So just to make sure we're on the same page, what I'm talking about is that the high band portion, which is this portion, this path, is fine. We're not looking at that. That one seems to be working. The low band portion, which then goes into the second converter here, doesn't seem to be working. So there's a couple of things that could be wrong with that, obviously. But let me change the color here. We now have too many colors. So what could be potentially wrong is that obviously we may have our mixers bad, because this is part of the equation there. We could have any of these things in this path going wrong. But given that our second LO power error was there, I am more inclined to think that something is wrong in this section right over here. So that's where I would like to focus my attention. So the A9 second LO board can be measured, and if you look carefully, I know there's many drawings now on top of each other, but if you look here, we are expecting to see a 3.6 gigahertz plus 3 dBm signal coming from this board. So this point I can measure, and this point I can measure. So you can see this was already one of the points I was suspecting, either of these two. So we should be able to do. Now there's an unlock indicator here, and I would imagine that if this was unlocked, that we would get an unlock error, but we're not getting an unlock error. So most likely this is internally locking. So it's becoming more and more exciting. So let's go and try measuring this, see what it tells us.
All right, let me give you a bird's eye view here. So what are we looking at? We are looking at the top of the instrument. This is the second LO board right here, and you can see this connector J5 right here. This cable is the second LO coming in at 3.6 gigahertz, and it goes around, and of course all around here, and it ends up in this right over here. So this is some kind of an oscillator board, and by the look of it, this most likely is kind of loose, huh? This is 600 megahertz coming in, and this is 3.6 gigahertz that's supposed to be going out. So this is an entire module itself, and most likely not made by Keysight. So we'll have to take a look once we take it out. But yeah, this is a great place to start. Now we could remove this cable. That should be pretty easy to remove, or we could remove it directly from here, and I suspect this is even easier. So let's go and take a look at this. We expect to see 3.6 gigahertz at 3 dBm. Pretty straightforward measurement. All right, let's do it. So we can go ahead and disconnect this. Now normally, obviously, needless to say that you're not really supposed to, you don't want to disconnect this while the unit is running, because sometimes these things don't like to be unterminated. But anyway, I know I'm not supposed to be doing this. I'm not patient. It takes forever for this instrument to boot, and I don't want to go through that. So anyway, we're disconnecting it. So here's the little makeshift thing that I made. So we connect that to here. Now we should be able to connect this to the spectrum analyzer. There we go. So it's nice. I don't have to bend the cables very much. And the spectrum analyzer is on. And there it is. So we expect to see, so let me just move this out of the way. We expect to see the 3.6 gigahertz signal as soon as I connect it. It's supposed to be about 3 dBm. So anyway, let me focus over here. I'm going to connect this cable directly to it, and let's see what we get. And here we are. Oh, I see something. And take a look at this. Haha, isn't that amazing? How's that for deductive reasoning? First point of measurement that we did, and we have a problem, of course. There it is. This signal is supposed to be 3 dBm, and it is minus 23 dBm. So the LO signal is not there. It doesn't have the correct amplitude, which explains the difference in the conversion gain between the two bands. That's why the noise was so low, because it wasn't converting, it wasn't doing anything. So there it is, and that perfect. So there we have a point of failure. We have a place where this could be an issue. So let's go ahead and take that out and actually have it on the bench. Because it is such a confined or such an individual unit just by itself, it should make it pretty easy to take out. So it's this one right here. So I can go ahead and remove it from the circuit. I can also tap it and see if the power changes. That would be interesting. Let me go ahead and tap it with my plastic pen over here. Let's see. Shake it around. Nope. Nothing happens. And I can do something else that's kind of interesting. I can remove the 600 megahertz reference to it. And let's see if I remove that, if that frequency shifts out of the way. You see? Yep, you can see it goes all crazy as soon as I remove the 600 megahertz. So indeed, it is doing something. Yeah. So there you go. Something is definitely wrong with it. So let's remove it, put it on the bench. We can test it by itself. That's the beauty of that. It's a self-contained unit. I'm eager to test it. All right, let's go ahead and take this out. I disconnected the cables, but there are many, many other cables that are in the way. Come on, you can do it. There we are. There it is. There is our board. And just like I thought, Elcom Technologies makes this. It is not made by Keysight. And this is apparently part of the second LO control as well as fan control, evidently. Yeah, so anyway, should be pretty cool now. Now, this is obviously completely independent, plus 12 volt, ALM, not sure what that is. ALM is alarm. Okay, so if it's in, for example, unlocked AFC, analog frequency control, I'm not sure actually. I don't know what that is, and ground. But I don't think we need these things to actually make it operate. If we power it, we should be able to get something out of it. And of course, we just need to give it 600 megahertz. According to the, yeah, there it is. And it also says 3600 megahertz. And the customer is Agilent, so they even have a sticker specifically for them. But there is a part number for this, S-1006A. So we might be able to get some information on it just by itself. And yeah, there's really nothing else to it. I should be able to test this completely by itself, just disconnecting it from this unit. Should be pretty interesting. All right, let's see what we can find about us online. And indeed, I found it right here. So nothing unusual, 3.6 gigahertz, the electric resonant oscillator phase lock loop standard source. Pretty clean, as locks to 600 megahertz, just like we expected. 100 dB C spurious, that's pretty good. And you know, used for SATCOM and so on, and digital radius to 512 QAM, blah, blah, blah. And over here, you can see some of the information about it. So it's supposed to work from 12 volts. It's supposed to take to less than 300 milliamp. We can verify that. And then the alarm option, TTL logic low for when it's locked. So indeed, the alarm is there. And yeah, I don't see anything else. Unfortunately, it doesn't give me what AFC is. I couldn't find any information about AFC. I don't think it talks about that. No, there's nothing in there about that. So anyway, but we should be able to power it on. Let's go. All right, here's my setup. Really quite straightforward. I have the output connected to the spectrum analyzer. 600 megahertz is coming from the synthesizer, and I'm connecting the 12 volts to the power supply. This is completely out of the circuit. We don't need to worry about that. We don't need to touch it. So over here, I have the spectrum analyzer, obviously, looking around 3.6 gigahertz, so we can see the signal. And here I'm set this to 600 megahertz at 10 dBm. So when I turn it on, we should have a reference. And over here, we have our power supply. So let me turn this power supply on. Put it on to high volt, and then let's increase this slowly. And you can see it's already taking current. And 12. Oh, not 13. Not 13. 12. There it is. 216 milliamp. That's within the specification. They were promising minus. They were promising 300 milliamp. So that's good. And you can see the power, the synthesizer is going crazy because it's not locked to anything, so it's going all over the place. So as soon as I enable this 600 megahertz, I expect this to settle down. So let's try that. And check it out, it locks perfectly, no problem. The output power is obviously way too low. The power consumption didn't change. It's still 219 milliamps from 12 volts. So yeah, it looks good. We should be able to do a quick measurement, maybe do a phase noise measurement on this. There it is. Here's the phase noise. Carrier is 3.6 gigahertz. They're obviously not locked to each other right now perfectly because the 10 megahertz of this is not locked to this, so the frequency is moving around a little bit from the point of view of the spectrum analyzer. But the shape is correct and it looks fairly reasonable. I can't remember the numbers, but I think minus 110 dBm around these, what is that, 2, less than 100 kilohertz. I think that sounds about right. So looks good, and the reason it flattens out obviously is because the signal power is too low. We're running into the noise floor of the EXA. But I'm pretty happy with that. If I turn the reference off, obviously we're going to lose lock. As you can see, the lock goes away. So indeed it is working. So pretty happy with that. So now the question is, what is wrong with it? Well, if the PLL is working, if it locks to 600 megahertz, if its power consumption is correct, if everything is good, the most likely cause is the output buffer of this thing is dead, of the synthesizer is dead. So by opening it, we should be able to take a look inside and see if we find out how it works. It may be some other issue, but I'm fairly confident that everything else is working in there. So I know what you want. You want me to take this apart? I also do. So let's go ahead and take the cover off and see if we can figure out what to do. And even if we can fix it, that would be amazing to be able to bring this unit up to speed with just such a simple problem. Although it may have some other issues. To be honest, it may have other problems in there we don't know yet, but it is definitely a step forward. Okay, here we go. I had to destroy the labels. I took a picture of it ahead of time, and it had many screws. I mean, just look at that. So here we go. What do we have? And ta-da! Yeah, lots of microwave design actually. A little bit surprised, but I see some things. I see some things that might be pointing to the right direction. So this looks like to be either a cavity filter or the dielectric resonant oscillator, most likely the DRO. Bunch of stuff here for the locking, I assume, and there's certainly circuits on the other side because I can see connections coming through. But the main output here is AC coupled, and we can see one amplifier there. We see definitely a filter there. This is why it has such good spurious performance, most likely a bandpass filter centered at exactly 3.6 gigahertz. Very cool. I gotta take a closer look at it, but promising, certainly repairable from a point of view of architecturally, because it's all discrete components. I don't see anything that's unusual, but we should definitely open the other side as well so we can see what exactly is going on. So let's go to the other side and we'll take a close look at it after. All right, and here we are. This is the module again, looking closely at it, and the architecture is fairly straightforward. We have our cavity here combined with this amplifier here, the transistor, and then this is our DRO section. You can see some small modifications there. Some of it might have to do with tuning, some of it might have to do with just modifications they made to the board, and power to the DRO section is provided from here. And going forward, we see an amplifier here, and then this is a doubler from Hittite, so which means that this entire section is working at 1.8 gigahertz, and that makes sense of why they have this filter afterwards, after the doubler, to create a nice clean tone from the doubled signal. So filter coming out of here somewhere, LC stubs, and they have 3 sections, 1, 2, and 3, which they can populate as they wish. And in this particular case, you can see that they have only populated this particular section here as an amplifier. This is going straight through. Here's our inductor, capacitor, bias D section, some resistor for biasing, some capacitor for decoupling. Going out, and here they put a 6 dB pad, which is the attenuator at the output there. Now this also improves the output matching and so on, so this is important. I don't want to remove that. And then you could have also, this can also be another amplifier. As you can see, this package is customized for use for multiple things. Yeah, pretty straightforward, nothing really unusual from that point of view. So therefore the DRO section, this oscillator has to only be locked from this portion at 1.8 gigahertz. The rest are just a feed forward section. And on the other part, we have all the circuitry required for biasing, the charge pump, phase detector, blah blah blah, all that stuff. I haven't really looked very carefully at it, but anyway, typical synthesizer architecture. Maybe they're using some other sections. I'm not really paying attention to it right now. I am concerned with getting the other section working. So yeah, pretty pretty straightforward. I may not be using a traditional PLL structure, but not interesting since the PLL is actually working. We can worry about that section later. So what is important now is to see what is going on here. So I suspect that, well, there's really no way to know, but I suspect that this portion is working. But we can probe it and find out if the levels of the signals are acceptable, and then from that we can find out if the signal before and after this amplifier is working or not. I suspect that this might be an issue there, or maybe the doubler even, and it's just not doubling very well. It's putting out a tiny signal here. We'll find out. This is labeled S1. I couldn't find it. I searched around for it. I couldn't find out what's going on with it, but we have plenty of places to do some measurements, and I'm sure we can learn something from this. So here I'm just checking the performance of my active probe. This is a 3 GHz active probe. It's an HP1, HP85024A, and I've had this for a long time, and obviously within its 3 GHz bandwidth is perfect. And I'm looking at it at 3.6 GHz. It has an additional 5.7 dB of loss. So it's not too bad actually, which means that we should be able to use it at least to make relative measurements to see if the amplifier is working, and that's good enough. We're not trying to make absolute measurements, but even for absolute measurements, this is pretty good right now because we know the loss. So for instance, if I change the frequency here back to 1 GHz, you can see that the signal level is very good. It's only 1 dB down, and I'm pretty happy with that. So this is good. We can use this to do our measurement and certainly probe it and power it on and see what happens to it. So let's set back up and see what's going on. Okay, we have everything set up and the active probe set up, so I have already applied the necessary signal to it, so we can start looking at what's coming out of the spectrum analyzer. So what I'm going to do is I'm going to probe a couple of locations. First, I'm going to probe the output of the synthesizer itself, the 1.8 GHz signal, which should be pretty strong. This noise that you see here, there's a source of 520 megahertz of signal somewhere in my lab, and I can't quite figure out where it's coming from. It could be from some of my home automation devices, but anyway, I have to find that out some other time. So ignore that tone, that's nothing. So I'm going to probe the output of the DRO just before the doubler. So here is just before the doubler, and we expect a large signal, and indeed we see it. Nice big signal at 1.8 gigahertz, minus 3 dBm. That's pretty good. So the DRO is working. Now the output of the doubler, we expect to see 3.6 gigahertz and somewhat attenuated. And the output of that, there it is. We see minus 20 here, which means it's actually minus 15 dBm. So it's not too bad. There's some conversion loss in the doubler. I have to check the data sheet to see if it makes sense. So minus 21 at the output. And the input, the signal is nice and large, minus 3. So minus 21, I have to give it a couple of dB. So let's say minus 18. So about 15 dB of loss or so through the doubler. You can check that. And then we go through the filter. So I pointed just to make sure that we're on the same page. I checked right before doubler, right after the doubler, and then we go through the filter, and we can measure that also. So we can measure the input and the output of the filter. So here's the input of the filter, which is the output of the doubler. And what do we see here? There it is. That's what we were just looking at it, minus 16 dBm. And on the other side of the filter, all the way to the other end of the filter, the signal is actually significantly smaller. It's minus 36 dBm. That filter, I'm reluctant to even believe that filter is that bad. Minus 36 dBm at its output versus minus 16 dBm at its input. So it seems like it has 20 dB of loss. That doesn't sound right, to be honest, but that's bizarre. But anyway, let's check the amplifier. So I'm going to check the input of the amplifier. The input of the amplifier is at minus 40 dBm, so that's pretty small. And the output of the amplifier is at minus 31 dBm. So the amplifier is presenting a gain of about 9 dB, which is itself also not very much. So yeah, it's a bit of a puzzling situation. Now there's a couple of issues that could be going on here. So first thing is, let's take a look at this here. As you can clearly see, it's very unusual to see this filter have so much loss. Now I do see a lot of discoloration on the surface of these traces. I wonder if they have oxidized very heavily, and therefore the lines are very poor in terms of the resistance, because it's the skin effect of these filters. So I'll try and clean it up and see if this is something that actually extends into the traces deeper, or it's just a surface contamination or a surface oxidization. But the signal coming out of here is loaded by this amplifier. Also, there's a series resistor there. So I wonder if this amplifier is doing anything to load the output of the filter, and the impedance is poor, and that's one of the reasons why we see that. So I'm tempted to remove this amplifier altogether and see if we get a more reasonable signal at its input when it's open. So then we can try and find out if replacing it would be worthwhile. I do have some different amplifier, I don't have that obviously, and see if we can maybe hack something in there that's similar in performance. But yeah, this is, yeah, you can see the colors are not very nice. They're not shiny like they're supposed to be. So the surface finish might have oxidized. I wonder. So that's another thing we can take a look at. So let me go and investigate this a little bit further, clean these traces, and see what happens next. So I went ahead and I removed that amplifier, the final stage amplifier, just to see what happens and to replace it. And I just also realized one other thing. I was making an error before. I had forgotten that I had my 10-to-1 attenuator at the output of my active probe while I was doing those measurements. So that's why some of those numbers were much smaller than we would have expected them to be. So the numbers are now correct. So just to show you what I mean, for example, the signal going into the doubler should be fairly large, and it is much larger than I was measuring before. You can see it's, it's very high, and it's in the orders of 15 dBm, which is what it's supposed to be. So this gives me some confidence that at least everything to the input of the doubler is good. And if I just probe the output of the doubler directly before the filter, we're getting minus 9 dBm coming out, and that's also not too bad, and it consists, it's about correct for what the conversion loss of the doubler should be. So I'm happy with that. The filter, obviously now I can't quite measure it the same way. If I look at the output of the filter now, I'm going to get some bad results because it's not terminated anymore correctly, so the impedances are all over the place. So I'll just go ahead and replace that with a different amplifier. Now this is going to be a totally different one, and this is going to be one of the amplifiers that I used before in one of my previous videos. I'm looking to see where I put it. Here it is, actually. There it is. It's right there. So yeah, this is an WBB320, I believe, T1, and it's in the this Micro X package type, which is exactly the same package. And these guys can go all the way up to 14 gigahertz. So they have a lot of bandwidth. They don't have a lot of gain, only 9 dB of gain. So we might have to even make more than one. Anyway, we'll see. I'm very curious to see what we can get with a brand new amplifier. Now the biasing of this is different than the bias network that's in here. In fact, if you look at it closely, the amplifier that's currently on the board is biased through a Darlington. This is a Darlington transistor here, and that Darlington transistor is connected to this through port, which goes to the other side at this standoff, and then from there it biases it. So there's a resistor, 55 ohm resistor in series with the output, which may actually be enough. It may work just as it is with our existing circuit. So I'm going to go and figure that out, put it in there. We'll do some additional measurements and see where it takes us. All right, so I did quite a lot of work on this and did a whole bunch of different experiments. And I tell you some of the things I found. First of all, as we measured before, I verified again with proper grounding, the probe and everything, and I got the same result. So the filter had a lot of loss. I mean, this thing has a huge insertion loss. And I suspect that it was because the material had degraded so much, and the surface roughness can be very bad for RF propagation because of skin effect resistance increases that accompany that. And if there's something else wrong with it, it might be. But the signal here was good, and the signal there has a huge attenuation, even when there was nothing connected. So I went ahead and I thinned this, as you can see now, it's shiny. I put solder on it, I cleaned it up, and that gave me about 6 or 7 dB back. But still wasn't enough. I couldn't recover the performance as it was expected. I replaced this amplifier, as you can see. I added some additional biasing that was required because it wasn't exactly matching. And then I went ahead and I removed the 6 dB attenuator at the output, and I put another amplifier in its place. So now we have 2 amplifiers in a row. And of course, it's not ideal. I don't have the perfect inductor, so there's some additional losses in here. But it doesn't matter. I just wanted to get this to reach a 3 dBm output power at 3.6 gigahertz, which is what it's supposed to do. Obviously, these modifications aren't ideal, but for what I had in my bin and just looking around, I think it's good enough for our purposes to go ahead and do some testing. So you can see I added some biasing here, and on the other side, I took some biasing directly from the power supply. I didn't want to overload this Darlington too much. But yeah, it looks good. Goes through there, back over here. nicely compact in there, so we should close it before we test it. Normally you don't want to leave them open for a final performance verification because these filters are tuned with the top taken into account, and everything else of course as well. So let's go ahead and see what happens. I made a lot of changes to this, and I'm eager to see how it performs, whether we would get our 3 dBm out and put it back in the instrument and do some more testing. Okay, everything hooked up just like before, and let's power it on. It's a bit of a mess in the lab now, so I expect it to consume a bit more power. You turn it on, there you go, yeah, about 270 milliamp. It was consuming about 220, so 50 milliamp extra from the second stage amplifier I added. And let's turn the reference on, and check it out, it looks good. I know I said I was going to close it, but I got too excited, so I didn't close it. But anyway, we'll close it up afterwards. But yeah, not too bad, I would say. As you can see, we have 2.66 dBm, 3.6 gigahertz coming out. There's some loss in that cable, so it's right around 3 dBm, which is perfect. And just to show you, I'm going to put the cap back on and take a look at the fundamental rejection there. And you'll see what happens when I put the cap on. Like that, and just me holding it with my hand. Check it out. You see the enormous difference it has putting the cap on the fundamental rejection from the doubler. It's quite extraordinary, isn't it? It's just because the filter takes that into account, so it's not properly tuned anymore, probably not properly matched anymore, and its characteristic is going to change. So we have to close it up completely, but now I'm fairly confident that this LO problem has been resolved, and we can put it back into the instrument, power it on, and try it. I'm very eager to see if we can bring it back to life. Well, check it out, it's all done now. So it went through the alignment, and if I go under system and go show errors, now you can see there's only one error, and then error is alignment step 20 dB. So there's something wrong with the attenuator, and it knows that it's not doing a 20 dB step, and we can try and see if that makes sense. So all the other errors are gone, which were preventing it from doing any of the other alignment. That's why we never even saw this. So let's go over here, and I have a synthesizer here connected to it directly. And this synthesizer is set to 1 gigahertz at 0 dBm. So let's go ahead and turn it on and see what happens. And here we go, and check it out. No problem at all. We can see our one, and it says 991 megahertz because I'm looking at it from very far away, but no problem. It's now showing a signal below 3 gigahertz, which it wasn't doing before, and the amplitude is correct. So I can go ahead a higher frequency. Here's 2, here's 3, 4, 5, and 6. And a little bit of that hump that you see here, I tried it with my other synthesizer, and I still see that hump there. Now it could be that we are actually still not meeting the harmonic rejection very well of that particular modification that we did, that we didn't really kill the 1.8 gigahertz very well. And let's see if that kind of makes sense or not. So if I bring this marker and put that marker, let's say here, and we can go ahead and reduce the resolution bandwidth. Yeah, let's put that here. It's actually not that bad. Oh, I'm changing the resolution bandwidth. That's not what I want to do. 1 megahertz, and let's go back to the marker and put that marker here, let's say, and then we're going to make a delta marker, and we're going to go over here and check this out over here, and no, it's about 1.5 gigahertz apart. It should be about 1.8 gigahertz. So yeah, I'm not so sure. I don't think it's because of that. I noticed some of that actually also on my other spectrum analyzer, so it's probably not from that. But anyway, I'll keep an eye on it. Looks good. I think it doesn't matter. I think this problem has been resolved as far as I'm concerned. So we can go ahead and reduce the bandwidth further, go very low, and we can let it sweep and see if we see any of that issue there. And yeah, it looks good. I would say this is a normal behavior, I think, and if I were to go ahead and turn off the synthesizer, you can see that some of that noise does go away and the noise floor gets better, and that's some of that noise is coming from the EXG, so some of it might be because of the harmonic of this. So anyway, it's something I can verify later, but nonetheless this is now back up and running. So let's go and see if this issue that we were seeing with the attenuator can be replicated. So let's go to 1 gigahertz and do a peak on this. And let's go ahead and change our input attenuations. Right now, the input attenuation is set to 10 dBm. Actually, you know what? Let me make this signal coming from the synthesizer much smaller. Let's make it minus 20, so this way we don't, or minus 30, so we don't overload it. There it is. So if I set the attenuation to manual and to 0 dB, you can see it says minus 30. That's correct. That's indeed exactly what it's supposed to be. And I'm going to keep going down. in attenuation, or up by attenuation, I should say. So it still says minus 30, still minus 30. So far, still correct. Correct, and we'll see at some point it's going to stop doing this right. There you go. That's our 20 dB attenuator, and that 20 dB attenuator is now wrong. It's reporting minus 10, which is obviously wrong. Now 22 is still wrong, and because the 20 dB attenuator is still engaged, at minus 30, it removes the 20 dB attenuator, and so our signal is back to the correct value, and increasing it is still okay. At 40 is still okay, so at 40 dB is not using that attenuator still. And 50, there you go, at 50 it must be using a 20 dB attenuator once again, so that value is wrong again. So we know what's going on. Yep, it's a 20 dB attenuator that's gone bad. It's not doing 20 dB attenuation. So what do? Well, we could replace the entire module. That's certainly one way to do it. The other way to do it would be to take the attenuator out and open it and take a look at it and see what's going on with it. Now, it does click in the 20 dB attenuator, so I wonder if it is the coil that's bad or if the contact is bad. Well, let's keep digging. We'll find out. So I just did a quick verification. I hooked it up to a different synthesizer. I hooked it up to the Tektronix one, and those humps are not there. So you can see the signal here sitting at 6 gigahertz right there at the same power, at exactly the same conditions. And I'm going to turn off the output power. And if you look carefully, you can see that the noise floor obviously goes down because the synthesizer generates noise, but those humps are not there. So those humps were characteristics of the other synthesizer. So it's fine, and so I'm happy about that. So the repair is okay. I shouldn't have to worry. Now what we need to do is we need to remove the attenuator and take a look at that one. So the attenuator in question is this one, A15, and you can see that it has a 10, 6, 20, and 30 dB sections. So this is a 20 dB section that obviously doesn't work, and we saw that with various combination of attenuations. So by having 2 dB here, 10, 6, 20, and 30, you can do 2 dB steps all the way through, and that's how we get all the 2 dB attenuation steps. So let's go ahead and take this out of the unit and see what we can do about it. All right, here it is. I took it out of the unit. This is the Agilent 33321-60058, and if you look at this, it's got type K connectors. I wonder if this is the same unit that is all the way up to 26.5 gigahertz, or I don't think it's the 50 gig version. No, it's not. For sure, maybe 26.5 gig version of this instrument uses the same attenuator, so this is not a cheap part. So I'd like to see if it can be repaired. So let's open it up, take a look inside it. I've actually done a full teardown of an attenuator before on my channel, and I've talked about how they work. So we're going to use some of that experience here and go from that. So let's see if this is repairable at all, and then we'll decide what to do. All right, here we go. I've disassembled it to the first stage, and I've shown something like this before, so it should be familiar to my regular viewers here. So here's a control for all of the different relays, and the attenuation section is embedded within this, of course. So the first step is to make sure that the 20 dB section is actually working, and you can see that by checking to see if the relays are going to be switching in and out or not. And we can use the instrument to do this. I do have a switch controller actually, but I don't have the right cable for it. So we're going to use the equipment to go through the attenuations. It doesn't matter that this is not inside the instrument. It's going to fail all the alignments at startup, but that doesn't matter. It will still be able to switch the attenuators, and we can see if the problem is with the drivers, the coil, or the attenuation section itself. And I'm eager to find out. All right, I've labeled the attenuation sections plugged into the instrument, and if you look very carefully inside this, and it's going to be difficult to show, but if you look very carefully here, you can see when the attenuator is not engaged. So this gap over here would be reduced when the attenuator is engaged. So each of them have that. So I'm going to demonstrate this. I'm going to start adding attenuation, and at some point when we hit 6 dB attenuation, the 6 dB attenuator is going to click. So pay close attention there. So right now we are 2, 4, and check it out. There, you saw that? So that's the 6 dB attenuator. It's working. You're going to continue 8 dB, and another 10 dB is going to kick in. There you go. 10 is down, 6 is up. Now we are at 12, 14, and then with 16, both 10 and 6 are both going to go down. There it is, 18, and then with 20, we expected 20 to click, but it doesn't. So the 20 dB relay isn't clicking at all, which makes sense why we were getting such a large signal, because it couldn't do it. So that's, now we know that for sure to be the problem. The 20 dB attenuator relay isn't working. That's actually a much better problem than the pad itself, because that's on the RF section, very difficult to fix. So let's go ahead and see what's going on. Is the coil open? Is the driver not working? You can see it's not clicking because it's trying to align. Of course it can't. So yeah, that's a pretty good result. Let's go ahead and see what we can do about the coil now. Well, that was easy. Turns out that the attenuator was only stuck. So I went ahead and I measured the actual resistance of all the coils, and they were all working, and these are Darlington drivers. So I was going to do some measurement on it, and I just kind of tapped it with my screwdriver, moved it around, and started clicking back and forth. I put now a little droplet of oil on all the pistons. So now it clicks, no problem. So that was lucky, a good, easy fix, and it was not a big issue. Hopefully it won't come back, but I think it's okay. So close it up, put it back together. Now we can finally test the instrument. And there we have it. Check it out. No more errors. And it is now a functioning unit. So let's put 1 gigahertz back in there. There's our 1 gigahertz tone. And this is sitting at 0 dBm. Perfect. So let me just move that down. I will put it at the bottom there so it's a little bit easier to see. And do another peak search. So let's reduce the amplitude here so we can do the same test again at minus 30. There's minus 30. You can see that it's showing it there and over there. So it is indeed a correct value with 10 dB attenuation, I believe. I can go ahead and change that. So let's set the attenuation to 0 dB. No problem, minus 30. We can now increase it 2 dB at a time. And it should always say minus 30. And 12, 14, 16, and then 18, and then 20 was the problem. Now it's not a problem, works perfectly. Minus 30, 22, 4, 6, 8, and 30 works. 32, 34, 36, 38, 40 was a problem, I think. Now it's fine also. And I believe there it is. And now it's getting close to the noise floor of the instrument, so we can go to minus 20 so we can see it better. And it is indeed also correct. The noise figure of the instrument is now huge. It's addition of 50 dB of noise figure added. So it's to be expected that it is like this. There you go. Do a preset on that and do a peak search, and it's beautiful. So let's go ahead to 0 dBm here. Now I noticed that this has a couple of personalities actually built into it. These are all the different things it has installed on it: channel power, occupied bandwidth, adjacent channel power, blah blah blah. And I think it also has no, I don't see it. Where is it? Measurement control, or maybe mode. There you go, mode. So spectrum analyzer, basic. I don't know what that is. Is it then? Oh, it has real time. Maybe does it? I don't know. It does kind of looks like it's doing something real time-ish. Interesting. So this is a pretty good. It's an input overload. That's too big. There you go. So that's cool. I gotta play around with that. I'm not sure exactly what basic means here in this case. Maybe it is real time. I have to check to see if that option is indeed installed, because if it has real time, that's a really expensive option. And then now it also has phase noise, which is great, and it has WCDMA, which is not that interesting really. So let's check the phase noise, and it should give us a log plot. Let me see, it's looking for the carrier. No, the carrier is not at 50 megahertz. Who measures phase noise at 50 gigahertz? There we go, 1 gigahertz, and then we'll put this into continuous mode. If I can find the button. Sweep, continuous, locating carrier, and it should do it. Yep, it did find the carrier. So let's get it to stop at 100 megahertz. And let it give us a nice phase noise plot. There we go. It's a little slow at the beginning, and it's going to speed up. And it's going to be the phase noise of this instrument, I believe, is going to be the worst case, because the EXG is pretty clean. So there you go. What do we have here? Let's say let's put it at 100 kilohertz offset. We're getting minus 121 dBc per hertz. I can't remember what the specification of the EXG is, but yeah, pretty good. So it's working. I'm very happy with it. Now we can do more experiments with it and so on and figure out what this basic is. I think it's real time. I have to check to see what options it has. But yeah, anyway, there you have it. I hope you enjoyed this repair. This was a reasonably complicated one. And I know that sometimes you guys don't like when there's just a power supply failure. I really don't control that, obviously. So I hope you enjoyed this one. This is a very nice instrument, obviously, quite an expensive instrument. And yeah, so I have a couple of other things. I have a few other little things that I need to repair. I have some reviews I need to do. It's just a lot of things. There's always something to do. And please let me know what you think. And again, thank you for my Patreon supporters. You're the reason why these are possible. And I can't emphasize that. As you can see, I've done a lot more repair videos recently because of that. So I hope that you can support the channel as well. Let me know what you think. I'll see you in the comment section.